Good evening, everyone. I hope I am coming through so far and that everyone is there. Dr. Mole, if you were not here last week, good to see you again. And I'm just making sure everything is up here and running. Good evening, everyone. I hope I am coming through. All right. So I hope I'm coming through. And if you're there, if you can just make sure that I'm actually broadcasting right now. Perfect. Thank you. All right. So I'm going to share the tab or make sure I got the right thing up and running here. And share screen. I think this is it. Okay. So a lot to get through tonight. And I am only checking my phone right now because I'm Valuable is contacting me. Lena is actually talking to me, making sure I'm coming through because I can't necessarily see the screen that is being presented, or I should say I'm not seeing the chat or anything. So, all right, making sure I got this up and going here. All right, I believe now the closed captions are on. Awesome, screen share is working, and I assume closed captions are coming through. Wonderful. So as we said last week, we're being recorded, and if you have a name that you don't want the whole world to see because it's just between you and your friends, now's the time to change it. Okay, so let's begin. Here is our social media, of course. And I also was asked to make a quick plug, if I can find it, our streams, our Psych Trivia streams. Let's see here. The next one will be at tomorrow at 10 p.m. I believe it's Eastern Time. That is AP Psych Trivia Review streams, 10 p.m. tomorrow. I believe that's Eastern Time. And if I got that wrong, I'm sure I'll get a message to the effect that I needed to correct something. So I hope you're able to make that. Retrieval practice, as we know in psychology, is remarkably important here. So let's jump into some content, shall we? You know, a lot of people are they're afraid of this unit. And you know what? When I was a little Dr. Mole, I was about yay tall, I too was afraid of this unit. I'm like, oh my gosh, you mean I have to know this stuff? I mean, even on my freshman year in college, and let me tell you right now, you are, I don't know what your status is in AP Psych. You are years ahead of where I was when I was a freshman in college. I remember learning about the action potential, the neuron, and I actually went up to my professor and I had the nerve to say, are we actually expected to know this? And the professor, much to his credit, was very tactful and just saying, yes, you are expected to know this. So, and really, when you really boil it down, it's just memorization of things. It's not like you're trying to balance, algebraic equations, or you're trying to solve or prove a theorem in calculus or something like that. So the major parts of this unit: the brain, neurons, and neurotransmitters, the nervous system, endocrine system, which is the hormones, and sleep and dreams. And I'd say 95% of this is memorization of terms. Obviously, I don't have that percentage calculated, but that's my estimation. So as we said, jumping right into this, we're going to start off with the neurons, the basic part of the nervous system. It breaks up or makes up the, these little quote unquote interconnected. I say the word interconnected very loosely here, but it's this network of structures, these little parts here that make up the entire nervous system. Now, the dendrites are on the receiving end. They're the ones that effectively receive messages from other neurons. And again, I've said this before, and I'll say this again. This is a gross oversimplification of the nervous system. A lot of things you learn about in AP Psych are oversimplifications, and this is oversimplification to the extreme. So if you do major in psych, and especially if you go into neuroscience, you start to realize there's a lot more to this. But right now, But I should say that when you get to a lot more to this, it becomes very manageable because you know the basics now. So the dendrites receive information from other neurons, and the neurons are sending the message, and the dendrites receive that information, passes through the soma, which we will call the nucleus of the neuron. Some say the cell body is the nucleus. Some say the soma is the cell body. But for our purpose, this is the soma located inside the cell body, the kind of the brain almost of the neuron. The message is then sent down through an electrical charge, a sort of neurochemical electrical charge down the axon. It's this long, thin structure that then sends out the messages through the terminal branches and releases these chemicals called neurotransmitters through the terminal buttons that those messages will go on to other neurons and pass on this message. Now, what's the message? Well, anything you think, do, speak, that's what I mean by the message. Again, we're taking very complex processes and breaking them down. So if I said, for example, I need to move my hand, okay, the message is move my hand, and it's actually a very complicated network of muscular movement and whatever. But the message to move is going down a series of neurons, many, many neurons actually, to get to my hand. It says move. Likewise, if I touch something, the feeling of it eventually gets to my brain as it goes through a network of neurons going towards the brain. So understand those parts. Dendrites receive the information. The soma is the nucleus. The message goes down the axon, and the message is then eventually released through the terminal buttons with neurotransmitters. There's some more visuals to kind of illustrate this point a little bit further. We're going to focus in on this axon here. And here we're talking about the axon at rest. Now, in this CRAM, we won't have the time really to talk about the action potential, other than just a few very basic ideas here. It's actually a very, very complicated process. But here we have the axon at rest. We have the axon here, and it's like this thin structure, and it has these blobs of fat, which we call myelin, and put it together, we call it the myelin sheath. And that myelin sheath coats and protects the axon. And the fatter or thicker the myelin sheath, the faster that axon can send the message down. The faster the axon can, the message goes down the axon. It's the only time where something gets there's more fat makes it faster. It's just one of those things where it's bigger, and here, boom, it actually goes down the axon much more quickly. So here you have a couple things going on here. At the axon that's in rest, when it's not firing off, when it's not sending off the message, you have potassium inside of it and sodium on the outside. And what eventually happens is, as that neuron fires down or fires off, as the message goes down the axon, long complicated story short and simple, potassium flows out and sodium flows in and kind of triggers this chain reaction going down. So that's where that falls into place there. So the thicker the myelin sheath, the faster the transmission. The nodes of Renoir is just basically little gaps, these little tiny gaps in between the little blobs of fat where the potassium and sodium flow in and out. That's all the nodes of Renoir are in that case there. So. Okay, so here we're now at the end of the axon, the end of the neuron. The terminal branch leads to the terminal buttons, these little knobs at the end of it that are filled with these vesicles, or have these vesicles filled with neurotransmitters, chemical messengers that send the message from one neuron to the next. Communication between neurons is chemical. In order for one neuron to communicate with another neuron, it has to send the chemical messages. Within the neuron itself, it's an electric charge. Okay, so as I like to say, communication between the neurons is chemical. Communication within the neuron, it's electric. Boogie, woogie, woogie. What can I say? I need to have some humor here this time of evening. All right, so the vesicles are full of these neurotransmitters. And when the neuron fires off, the neurotransmitters are released into the synaptic cleft. And like some horrible drama or romantic story or something like that. The terminal buttons try to reach their love of their life, the receptor sites. Those neurotransmitters try to bind to a receptor site where they can bind, and then they can fire off. So, and if enough of them bind, that's great. You see these neurotransmitters, enough of them have to bind to receptor sites on the postsynaptic neuron, the dendrite of the next neuron. So you have the terminal button on one end that's sending the messages through the chemicals into the synaptic cleft, the gap in between, because neurons don't actually touch each other. They get really, 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 really close, but they don't actually touch each other. So the message is sent out with these chemicals in the synaptic cleft, and enough of those chemicals bind to the receptor sites on the dendrite of the postsynaptic neuron that fires off. Great, wonderful. Now, some of them will bind to receptor sites. Some of them will drift out of the cleft and eventually be broken down by enzymes and become amino acids. Some might get pre-absorbed into the presynaptic neuron. They get resucked up like a Hoover vacuum cleaner, go back into the terminal button, a process called reuptake. That term is right there on the lower right-hand corner. Gets reabsorbed through reuptake. It is an all or none response. In other words, either the neuron fires or it doesn't fire. A neuron doesn't kind of fire, much like a gun doesn't kind of fire. I mean, misfires notwithstanding. A light switch doesn't kind of turn on the lights, dimmers notwithstanding. A light either goes on or goes off. A neuron either fires or it does not fire. So a certain amount must bind in order for that firing to occur. Now, there are many different types of neurotransmitters, and a neurotransmitter will only fit a particular receptor site. How many neurotransmitters there are, scientists debate. The complicated nature of how the chemicals bind and why only some bind to certain types goes well beyond the scope of this course. But understand that as the neurotransmitters are released to the synaptic cleft, they have to bind to the receptor sites, and they can only bind to certain receptor sites. It's like a lock and key mechanism. As a matter of fact, that was a question I believe that was once asked on the AP exam. The neurotransmitters binding to the receptor sites are much like like a lock and key mechanism. So there are chemicals that mimic neurotransmitters. They're chemically similar to neurotransmitters, and by introducing those chemicals into the body and into the bloodstream, into wherever, the idea is that because they're chemically similar to neurotransmitters, they will bind to those receptor sites. So agonists are chemicals that mimic neurotransmitters and can bind to receptor sites just like the neurotransmitter can. And because there's more binding, in theory, there is more action potentials as a result. More action potentials occur, which translates to, in theory, more activity in that part of the nervous system. So agonists mimic neurotransmitters. On the other hand, there are antagonists which block neurotransmitters, where essentially the antagonists, in a way, bind the receptor cells or receptor sites, but they don't actually bind. They kind of block them. Again, taking a complicated process and simplifying it, so that the neurotransmitters don't bind or can't bind, making the neuron less likely to fire. And because it's less likely to fire, meaning that there is less activity. Now, depending upon the situation, sometimes you want more activity, sometimes you want less activity. And, that goes right now beyond the scope of this unit. But, basically, every illicit drug, be it marijuana, LSD, cocaine, and many psychotropic medications aimed to treat mental health conditions, basically work in that one or two ways. Either they work as agonists or antagonists. There's other things too. SSRI, selective serotonin reuptake inhibitors, in theory, they try to stop reuptake from happening of serotonin, so there's more serotonin in the synaptic cleft that will bind and fire off serotonin receptors, which in theory are supposed to elevate mood. That theory has been very widely debated right now, and there's a lot of people who are kind of dispute that, but that's a different story. But that's the idea behind SSRIs, at least. Now, there are many different types of neurons, but for our purposes here, we'll talk about the two major types here. First, sensory or afferent neurons. They are messages that go towards the central nervous system, towards the brain and the spinal cord. They're called sensory because what goes towards my brain? Well, it's usually what I'm feeling, like literally with my skin. Obviously, there's my ears and my eyes and everything else. But for the simplicity's sake, we often think about in terms of the sense of touch. I touch something on the hot stove. That message goes towards my brain and spinal cord, and it's through those afferent neurons. There's actually more than just that, but for our purposes, we'll say the afferent neurons sending the message towards the central nervous system. A for afferent, A comes first because you need the input first. A for arrive, some people use that mnemonic. Whereas motor neurons or efferent neurons, they are messages that carry away, messages that go away from the brain and spinal cord to the parts of the body. So I need to wave goodbye. Okay, in order for that to occur, my brain has to send a message to my arm and my hand, to all the muscles and everything else to move in order to make that waving motion goodbye. That requires efferent neurons. E for exit, E for efferent. Efferent sounds like effort, takes effort to move response. To respond, there are many mnemonics here that hopefully can help. So, all right. There are many types of neurotransmitters. The exact number is debated. For our purposes here, we'll stick to 6. Acetylcholine enables muscle action. It's associated with learning and memory, also attentiveness. One mnemonic here is that the ACH is in macho man, someone who is strong, someone who has a lot of muscles. Although have muscles takes a lot more than just acetylcholine. There's other things as well. Even if you don't have a lot of muscles, you're still using acetylcholine to move. Okay. Dopamine is associated with voluntary movement. Now, you see, acetylcholine helps you move, but dopamine helps the movement be controlled and more precise. The fact that I can touch my nose like this, okay, to move the muscles, I need acetylcholine. To make them controlled, I need dopamine in order to make it a much more precise movement. Again, that's simplifying things here a bit. It's also associated with pleasure, associated with the reward center of our brain. Taking certain types of illicit drugs basically stimulate dopamine receptors as if there's more dopamine in the brain. Serotonin is associated with sleep, eating, and mood. Also attention as well. There's 2 O's in serotonin. That is, which same thing with mood. Some people use that as mnemonic. It is classically associated. Low levels of serotonin are associated with depression. This has been very strongly debated. This is a back and forth debate that just goes on and on and on. And there is because then it also relates to antidepressants and how antidepressants work, and it's a very, very ongoing, intense debate about that. But for our purposes here, it's said that low levels of serotonin are associated with depression. Norepinephrine, not norepinephrine, but hey, call it whatever you want because there's no speaking test here. Controls alertness, arousal, mood. Agonists create euphoria. Certain drugs try to up the norepinephrine to make one more alert, more aroused, to have a better mood. GABA is an inhibitory neurotransmitter. Let's see, do I have a Slack message? No, I don't. Okay. Basically, what's happening there is again, really simplifying things. Generalized anxiety disorder is often associated with an overactivity of neural activity in the brain. Again, really taking a very complicated disorder and simplifying it here for our purposes. And GABA tries to slow things down. So, for example, certain anti-anxiety drugs, such as Valium, try to up the amount of GABA in the brain to slow things down. Again, that's really simplifying things there. So, but the way I remember it, think about Fred Flintstone, yabba yabba do, gabba gabba don't. It's just the way I remember it. Hopefully it works for you. And if not, hey, I tried. Glutamate is an excitatory neurotransmitter. It is associated with memory in a way. And it's also, we know that some people have a gluten sensitivity, for example. Too much glutamate can lead to migraines and, in extreme cases, seizures. That's why some people might need to have watch their diet and watch gluten. It's a very small percentage that actually need to do that. So it's not common, but for some people, too much glutamate can be bad because they have a sensitivity. All right, now we're going to talk about different parts of the brain. So here we are moving more towards the actual brain parts themselves. So we start off with the medulla. The medulla connects the brain stem to the brain itself. It is in charge of the most basic life functions: heart rate, breathing. This is the part where if damage is sustained here, it can cause a very high probability of death. You know, if a person got sustained damage to the, say, the middle of the brain or the front of the brain, chances of survival are pretty good relative to taking damage to the medulla, because it could mean instantaneous death because of the most basic life functions are held there. Moving up, we talk about the pons. The pons is associated with sleep and arousal. And again, a lot of these brain parts do many other things. Again, we're simplifying it here. Pons associated with sleep and arousal. I often like to think about sleeping by the pond. And by the way, there's a lot of teachers who have mnemonics, these same exact mnemonics. I kid you not, like sleeping by the pond, I honestly thought of myself, but so did other teachers independently. So, but hey, in education, everything you hear has been copied from someone else. So it's not like I sat down one night and thought of these all by myself. These have been said time and time before. So medulla, this one I did think of myself. But so few students could actually connect to this one. But I watched professional wrestling growing up when I was a kid, and there was a very famous lady wrestler named the Fabulous Moolah. And if you have no idea, then just tune out for the next 5 seconds. But basically, I think about the fabulous medulla putting on a sleeper hold on someone, cutting off your blood. Your blood flow and breathing. So just the way I remember it. So, all right. So the pons, sleeping by the pons, is your sleep and arousal. The reticular formation is, it's actually located here behind the pons. It is still in this pink area. It's actually, so if you have the pons being the big circular thing, the reticular formation is kind of right behind it. It assists the pons in sleep and arousal. It also helps us with attention. It also helps filter out irrelevant stimuli. Right now, I hope you're focused on what I'm saying and following as best as possible what I'm saying. But if there's a TV in the background, or if your brother or sister's there, let's say, and they're talking, you might be able to filter that out because you are focused on what I'm saying. The reticular formation helps you with that. We now move into the cerebellum. So we're moving up in the brain. Pardon me here. We move up just a little bit. The cerebellum helps us with balance, fine motor movements. Fine motor movements mean, like, for example, moving my arms like this is a gross motor movement. But to be able to touch my nose like this, to pluck the strings of a guitar, to write with a pencil, require very minute and precise movement. And the cerebellum helps me do that. It also helps with procedural memory, how to do things. Now, when we get to, I believe it's Unit 5, we talk more about memory and things like procedural memory, but how to do things, how to play the piano, how to kick a soccer ball, how to drive a car are all part of the cerebellum. Other parts of the brain also play a role, but the cerebellum plays a major part. Some people talk about my good friend Cerebellum, who's a very clumsy person, keeps tripping over because she has no balance. Again, hopefully that works for you. If not, hey, I tried. Okay. The hippocampus is, and by the way, people say, like, do I have to remember the exact parts of where each brain part is in order for me to, like on the AP exam itself? The short answer is yes, but it comes with a kind of a good thing going for you. So let's say they gave you this here and say, what, and they'll say, they said, what part of the brain is this? And pointing to the hip, where is actually the hippocampus. They would give you choices like medulla, frontal lobe, reticular formation, cerebellum, things that would be obviously wrong. They wouldn't give you, let's say, hippocampus and probably amygdala also as a choice. They probably would not, because it would be very hard to actually put on a black and white figure. Now, it's possible they could, and it's, in that case, probably a lot of students will get it wrong because sometimes it's, they're so close together. And if that's true, then a lot of students get it wrong. And in theory, the cut scores for what you need to get a 5, 4, 3, and so forth go down in theory. So the main takeaway is don't get too caught up in the the actual particularities of one versus the other. Know the general areas, more or less. So the hippocampus helps with the most memory formation. Like I said, like procedural memories go through the cerebellum, emotional memories go through the amygdala, more on that later on. At Camp Hippo, memories are made, is what I tell students. At Camp Hippo, memories are made. And if I had the rights to show it, there's this little GIF I have of two hippopotami kind of like snuggling with each other in being romantic, and there's a little sign that says Camp Hippo, where memories were made, and I have the song Unchained Melody playing in the background. That's what I do for fun, making slides like that. But but Camp Hippo, where memories are made. The amygdala, where it's emotions and emotional memory. So yes, we have memories, but there's some that have strong emotions attached to it, associated with anger or fear, perhaps intense excitement. All those things are kind of processed through the amygdala. Of course, the hippocampus will play a role, and sure, so will the cerebellum. But primarily, for our purposes, we'll say emotional memories are processed primarily by the amygdala. Okay. Moving on, we have the hypothalamus, which for some reason the arrow is way off here. I apologize for this. I don't know what went wrong there. But the hypothalamus, so here you have the thalamus is in the middle. The hypothalamus is actually, it's right below it. It's, and again, so long as you know that the hypothalamus is kind of just a little bit below the thalamus, that should be good. I apologize for this arrow being way off here. But essentially, the hypothalamus, located right below it, it's in charge of the 5 F's. The 5 F's, as we say, it's like here, they are feeding, fighting, fleeing, Fahrenheit. So let's start off. We have feeding, which is essentially our appetite. Fighting, the fight or flight response, which basically we have an emergency, we can high gear. The fight or flight response, which is our emergency survival system. Fahrenheit, which is our body's temperature. The body's temperature is regulated by the hypothalamus. And mating. Yes, that doesn't begin with F, but textbooks like to make a joke about this. It's the 5th F is mating. And in case you're wondering what the 5th F is, it's fornication. That's the joke we often say in AP Psych right there. So basically reproduction is also associated with the hypothalamus. Again, other parts of the brain play major roles, but here we're talking about the major, most basic parts here. All right. The thalamus is right there. It's pointing to, it's above the hypothalamus. It's our sensory relay center. When my eyes see something, my thalamus says, okay, send that to the occipital lobe. When I hear something, my thalamus says, okay, send that to the temporal lobe. Happens with all the sensory information with the exception of smell. Smell is always the exception to things. More about that in the next review. But for there, we'll leave it there for that for now. Let's talk about the different lobes here. The frontal lobe, right smack dab in the front. Who said AP Psych was hard? It helps with movement and decision making. Again, lots of other things here, but for our purposes, the ability to move is in the frontal lobe. Decision making is in the frontal lobe, particularly in the prefrontal cortex, which is really in the front here. Helps us with decision making. The parietal lobe, located approximately here, is the sense of touch. Again, way oversimplification here, but for our purposes, it works. It has what's called the somatosensory cortex, which is specifically aimed at the sense of touch. That word, actually, that term, somatosensory cortex, appeared on the AP exam about 5 years ago or so, and threw off a lot of students. It just basically is in the parietal lobe, helps with the sense of touch. The temporal lobe, this makes sense, is not far from our ears, helps with the sense of hearing, helps us process auditory sound. And whether you believe in God, evolution, both, neither, or something else, however we came to be, had a sense of humor, because when it comes to the sense of sight, it would make sense that, well, whatever we see should, our brain should be very close to our eyes in order to help us process vision. But for whatever reason, what we see is processed all the way in the back of the brain in the occipital lobe. The back of the brain, it's the occipital lobe, helps with the sense or the sense of sight, processes visual images. I think O for optics, O for occipital. Okay, we are looking at the left-hand side of the brain. Now, this applies to almost all right-handed people, and I believe a majority of left-handed people. But for some, it's going to be switched. Why this is another discussion. But as far as the AP exam goes, this applies to everyone. In the left temporal lobe, you have in the front side, kind of the frontal lobe, some say frontal, some say parietal, Broca's area. Broca's area helps with language production, the ability to speak, the ability to write, to express ourselves in terms of language is used with Broca's area, whereas Wernicke's area, found primarily in the temporal lobe, helps us with language comprehension. That's Wernicke's area. So Broca's area helps us express ourselves in terms of language. Wernicke's area helps us with language comprehension. Understand that, like I said, this is a simplification here. If a person took damage to Broca's area, they might be unable to speak or unable to write, or both. A person with damage to Wernicke's area might be able to speak just fine, but they literally would not make much sense at all. Similarly, they would have difficulty understanding what you are saying as well, that because of Wernicke's area is damaged. Okay, so again, like I said, we're moving through a lot of stuff in 1 hour. It's quite a bit. Here is the endocrine system. The endocrine system refers to the hormones in the blood, whereas the nervous system, where it was chemicals in the brain and spinal cord, here we're talking about chemicals in the blood. Now, some neurotransmitters are also hormones because they exist in the blood. Which ones are not terribly important for this unit. As a matter of fact, in terms of what you need to know for this unit, it's actually a little bit different than actual neurotransmitters. And actually, not many hormones need to be known for this at all, as it turns out. So we start off with the pituitary gland. The pituitary gland, and again, the exact locations here, if they ask you where it is, they will be, it says, what is this? And the answer is pituitary gland. They would give you other ones that are obviously incorrect. You can see it's obviously not the pons because it's that big thing that kind of swells on the spinal cord. The medulla is up below that. Cerebellum is in the back. I'm sorry for the yawning. So they would give you ones that are, that would be blatantly correct. It's in charge of our growth, helps us grow. A person with an overactive pituitary might grow too quickly and too much. And it's also the pituitary gland that's in charge of, it's kind of like the master gland. It's the manager of the rest of the endocrine system. The pituitary gland is actually controlled by the hypothalamus. So in a certain sense, the hypothalamus is like the owner of the endocrine system, and the pituitary gland is his manager. So, so the pituitary gland helps us with growth. It's the master gland. And for those of you who may remember the show or the movie The Princess Bride, Andre the Giant was known for having an overactive pituitary gland, and because he was so large, it eventually led to his death at a relatively young age. And of course, he was also a well-known professional wrestler. All right. The thyroid gland is located right here. It helps with our metabolism. A person with an underactive thyroid might have difficulty, especially with weight. That happens sometimes, but it helps with metabolism. Releases a hormone called thyroxine. Thyroxine helps us with metabolism. But again, there's a lot more to regulating weight than just thyroxine in the thyroid gland, but it helps us basically break down our food and convert it into energy. The adrenal gland, located basically right above the pancreas, roughly about here, let's say, gives us emergency energy. Among other things, it releases adrenaline, or also known as epinephrine, which is why if a person has a severe allergic reaction, they may have an EpiPen, which is basically a shot of adrenaline, try to get the body to fight against the allergen. Again, simplifies the process here, but that's the idea through it, or to it, I should say. The pineal gland is kind of more in the brain. It's right not that far from the pons, as you can see. It helps with sleep and releases a hormone called melatonin, which helps us with our sleep cycle. So the pineal gland helps us with sleep, and with melatonin helps us regulate our sleep cycles. The pancreas helps with glucose regulation, glucose being the hormone, or I should say being sugar, insulin being the hormone that breaks down the glucose or helps regulate the glucose levels so that we have the right amount. A person with diabetes, long story short, has a condition where their pancreas is not providing the correct amounts of insulin to regulate glucose or sugar. That's why they might have to take insulin shots from time to time. The gonads are the reproductive organs of the body. They help with basically reproduction. With the females, it's the ovaries, which produce primarily estrogen, and the males is the testes that produce primarily testosterone. It was once thought that that's all they ever produced, respectively, but as it turns out, the ovaries do produce very small amounts of testosterone, relatively speaking, and the testes also produce relatively small amounts of estrogen as well. So they do produce both, but primarily the ovaries are producing estrogen and the testes are producing primarily testosterone. All right, we're moving into now here we're talking about measuring brain waves. We're talking about how do we study the brain. We have the EEG, which is the electroencephalogram. It's a way of studying brain waves of the brain. And there's different brain waves that correspond to different things. Now, why we have brain waves? Basically, brain waves correspond to activity of the brain. And when there's beta waves, okay, so basically an EEG, if you've never had experience with it, they put a bunch of electrodes, depending upon the EEG, there could be as few as 2, there could be as many as 60, 70, 80, if not more, to monitor different activity of the brain. When there is beta waves, that means there's more or less, a lot of neurons firing off in that particular area of the brain. And there's a lot of activity. Beta waves associated with being awake and alert. When there's beta waves, again, I'm really taking a pretty complicated process here and kind of simplifying it here. When there's beta waves, you're talking about being awake and alert. So there's a lot of beta waves going on in your brain. There's all these other waves going on too, but when you're awake and alert, there's a lot of beta activity going on in your brain. In other parts of the brain, there might be different brain activity, but what we're going to say here is that there's primarily beta activity going on. With alpha activity, this is being associated with being awake but relaxed. You're still awake, but you're relaxed. You're sitting down, you're watching television, maybe you're reading a nice book, listening to some comforting music. You are there's primarily alpha going on in the brain. Theta is associated with light sleep, just falling asleep. There's a lot of theta activity going on in the brain, and delta waves are associated with being deeply asleep. Activity of the brain is very slow. It's active, but just not as active compared to the other states that you're in. There's also something called gamma, which is like excessively alert, but the AP curriculum typically doesn't go into detail about that. If it were to be there, it'd be above beta. But these are the 4 brain waves that the AP exam typically works on there. So a person goes to sleep. A person goes to sleep at night, and it's not a dichotomy of being awake, asleep, awake, 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 asleep. There's actually different stages of sleep that go on when we dream or when we are asleep at night. So stage 1 sleep is associated with being it's the first stage of sleep, and it's a weird stage of sleep because you think you are still awake. Here I am, my eyes are closed, and I can still hear what's going on, and I still feel like I am awake. Yet, if I'm hooked up to an EEG, I'm showing signs of stage 1 sleep. What happens here? This is, and you might experience this. So you're falling asleep, you're falling asleep, and suddenly your arm or leg jerks all of a sudden, so much so that it might even jerk you awake. And you're like, oh my gosh, what was that? And if you ever had that and you got afraid by it, I guarantee you it's a very normal thing. They are known as hypnic or myoclonic jerks. Hypnic or myoclonic jerks, they are completely normal and they do happen. Also, you might get what's called hypnic imagery. You're closing your eyes and you might see flashes of light or maybe images of your day being replaying, or some people describe it as a kind of a pseudo dream. Hypnic imagery happens during this. So during stage 1 sleep. So if your arm is jerking and you're having this imagery, you actually, I had students say to me, oh my gosh, I was in stage 1 sleep and I recognized it. And I even told myself I was in stage 1 sleep. You also know when you're in stage 1 sleep when like you're trying to fall asleep, mom or dad or whoever walks in the room and asks you a question and you start talking and it's like very mumble, like, oh, wow, this is not making sense. Probably means you're in stage 1 sleep when that's happening. Stage 2 sleep. Here you basically lose awareness, quote unquote. You're still aware even when you're deeply asleep. You're still aware, just it's not quite as active as when you're fully awake. Here, the two things about stage 2 sleep are more associated with the EEG itself. Pardon me. The sleep spindle is a burst of brainwave activity, the brainwave, and suddenly it's like very, very quick brain activity. What happens during that sleep spindle is not entirely well understood, and for our purposes, not necessary to know for the AP exam. But no, it's a brief burst of brainwave activity that happens during stage 2 sleep. It's called a sleep spindle. The other thing called a K cluster being basically one or two very big waves that usually correspond to a loud noise. So you're asleep and there's a clash of thunder or someone drops something near you while you're asleep. There's that big brainwave that kind of reacts to that big noise or that big distraction. It's called a K cluster. It happens during stage 2 sleep. Now, depending upon how old your textbook is, some would say that there are 4 stages of sleep, which is what we're talking about here. Older textbooks might describe it as 5. For our purposes, we're going to stick with 4 because that's what the AP exam tends to reflect on, to my understanding. Because what the older textbooks call stage 3 and stage 4 sleep are so very much alike or have so much in common that the differences are very, very small and kind of beyond the scope of the course. So with stage 3 sleep, you're just in deep sleep. You're just in deep sleep or deeply asleep when that occurs. REM sleep, rapid eye movement. This is a stage of sleep that happens. It's kind of called paradoxical sleep, and you'll find out why. Because a couple things happen. REM stands for rapid eye movement. It's where when you're in REM sleep, your eyes are moving all about, and they have special equipment that can look at your eye movement and whatnot. And so what's happening there is it's monitoring your or monitors your eye movement. And what you find is when you're in REM sleep, your eyes are kind of like, if my eyes were open, I'd be like looking all around the place, but your eyes are closed. And sometimes if you see a person in REM sleep and they're sleeping, it looks like a wavy motion of their eyelids because their eyes are moving all about. So that is rapid eye movement. During REM sleep is when you are dreaming. You're dreaming at night. So if a person's eyes are darting back and forth while they're asleep, chances are they're dreaming at this point. And what's weird is that the brain is active. It's almost as active as when you're awake. Almost as active as when you're awake. So you have your eyes darting all about. Your brain is very active, producing all this rich imagery. But yet at the same time, there is no movement below the neck. You can't move from the neck down. So it's very strange. So while your brain is so active and your eyes are moving all about, your body can't move. Well, I mean, if there's an emergency, you can jerk yourself awake, but your brain, you're basically not moving. So you see on the TV shows, the movies, people have these very, very rich, elaborate dreams, and they're sleepwalking or they're kicking and punching while they're having this really intense dream. Doesn't happen. Because if you're actually having a dream or a nightmare for that matter, you're not moving from the neck down. I'm talking about rich, elaborate dreams. If you ever had a nightmare, like a really, or a dream, where it's like a really rich, deep story, usually when you wake up, your eyes are open and you might notice your body's actually very tranquil. That's because you were in REM sleep. Your body was not moving from the neck down. Sometimes they call stages 1, 2, and 3 non-REM sleep, and then the one being REM sleep. All right, so if you were to look at EEG, you don't have to memorize this exactly or anything like that, but just understand that as you get into deeper, deeper sleep, the brain waves get bigger and there's fewer of them, let's say every inch. But when you go into REM/dreaming, there is quite a bit of activity going on there. So, a person says, gosh, I must have slept very deeply last night because I was dreaming very much. Well, no, because if you were dreaming a lot, you were actually, your brain was actually quite active. You were not in deep sleep. They are two completely different opposite things that occur there. A couple of distinctions between REM and non-REM sleep that you should keep in mind here. And I kind of touched upon some of them. With REM sleep, there's none from the neck down. With non-REM sleep, it is possible. Dreaming, you might have rich imagery and it's a long duration, whereas there's none, or you might have a very brief, fleeting image. So let's say you did wake up and you jumped up. Usually what happens right before is a very brief thing. So like maybe I had a dream, not a dream, but I had this image while I was asleep that I was falling and then suddenly I jerked myself awake. That could happen because that can happen during non-REM sleep where the body can move. But if I had this long, this dream where I'm flying, let's say, I'm not doing this with my body because in REM sleep, I can't move from the neck down. The timing of it, it gets longer. The more we sleep, there's more REM as we sleep. REM, we go in and out of REM and non-REM. As we sleep. And as the night goes on, there's the periods of REM get longer and longer, and the non-REM, as a corollary, gets shorter the more we sleep. And this is a visual representation. This visual happens to reflect a 5-stage sleep, but you can, for our purposes, put stages 3 and 4 together and count as one deep sleep thing. So with this here, as time goes on, there's less and less deep sleep, and the REM sleep tends to get longer as a result. We tend to there's also developmental aspects to this. The amount of time that we sleep and the amount of time we spend in REM. Notice that when we're born, the first couple of days of life, we're sleeping almost 16 hours a day. That's quite a bit. But as time goes on, we're sleeping less and less. And let's see here. For everyone here, you're about 14 to 18 years old. According to this, you should be getting about 10 hours of sleep a night. I'm sure everyone's getting 10 hours of sleep a night. I'm sure that's happening. And I'm sure especially when before all COVID was happening, I'm sure you were getting 10 hours of sleep a night all the time too. Well, in theory, so if you're getting your 10 hours of sleep a night, you could see about 8 of those hours are in REM sleep. And as we go older, the percentage of time we spend in REM goes down, as does the amount of time of sleep that we need as well. So there are developmental aspects, age aspects of REM sleep versus non-REM sleep. There's also this interesting phenomenon where, let's say I do an experiment where I hook you up to an EEG. And I deprive you of REM. It's called a REM deprivation study. And what I do is I have you sleeping, and every time you go into REM, I wake you up. Basically, I try to, by night 7 or 8, I try to curtail the amount of REM that you're in. And this happens for a day or two. And so then what happens is the next night, I allow you to sleep uninterrupted, and you can sleep as much as you need to. I'm not going to interrupt it. What you find is that you compensate for the lost amount of REM by spending a lot more time in REM. This is referred to as the REM rebound effect. Here, when you have the REM rebound effect, this is where you are deprived of REM sleep, and in this case, it's selectively done. Sometimes you might notice that, let's say you sleep pretty terribly for a couple of nights for whatever reason, and then you go to sleep, and then you find that you were dreaming quite a bit that night. Kind of the idea is that you are having a REM rebound effect. That could be possibly what's going on there. So that's the REM rebound effect. Problems as to why we sleep, what causes sleeping problems, or I should say what type of sleeping problems that we have. Some of these you don't have to be told the definition, but I'll still tell you anyway. Insomnia refers to, a difficulty of either falling or staying asleep. Difficulty falling asleep or staying asleep. So I lay down in my bed and I can't I can't fall asleep or I can't stay asleep, and that's a problem. So that's insomnia, the difficulty of falling or staying asleep. Now, narcolepsy is often referred to as having what might be called sleep attacks, where a person is awake and suddenly they fall right into REM sleep. Again, we're talking about the classic textbook manifestations of this. There's variations of it where it's not quite so abrupt, but for the textbook presentation, they're awake and then suddenly they go right into REM sleep. And because you can't move from the neck down, if they have a sleep attack, they could literally collapse to the ground and go right into REM sleep. It's not a comforting sleep. It's not a restful sleep. It might last for a couple minutes and they kind of wake themselves back up. It wasn't very refreshing. So yeah, you have that goes on there. And I have a friend who has narcolepsy, and for her, it's more like she's just very tired quite often throughout the day. So, but that's the textbook presentation of narcolepsy. Sleep paralysis is where a person is in REM sleep and they wake up and they find they can't move. Now, sleep paralysis, a person who has sleep paralysis will often report, oh my gosh, I was having this weird hallucination in front of me, weird that I was seeing these things and I couldn't move. Well, what's happening, to make a long story short and simple, is that you're basically part of your brain is still asleep. Part of your brain is awake. That's why you're looking around and aware of everything that's going on. But part of your brain is still asleep, and namely in REM sleep. And because you're in REM sleep, well, you can't move from the neck down. No wonder why you can't move. And because part of it is still in REM sleep, you're still having that imagery associated with dreaming. And so you're literally having a dream while awake. And sleep paralysis, while not dangerous, can be very disconcerting for those who have it. Sleep apnea is difficulty breathing while asleep. The airway isn't very clear. It could be due to smoking, obesity, diabetes can contribute to these things. And if it's severe enough, a person might need to have a mask in order to get oxygen into the lungs so they can sleep better. So, and then somnambulism happens during non-REM sleep because this is associated with sleepwalking. It's not always going to be sleepwalking, but it's the most classically associated thing. A person might walk in their sleep, and it's happening during non-REM sleep. A person's not sleepwalking and having massive dreams or anything like that. So it happens in non-REM sleep. So that's somnambulism. It's non-REM sleep. Okay, dreaming. This is actually Freudian terminology here. Manifest content and latent content. Manifest content is the content where you're actually dreaming, whereas latent content is the hidden meaning within it. So I dreamt that I was going on a trip through Europe and I saw this, that, and the other thing. And someone might say, well, the meaning of the dream is X, Y, or Z. And therapists really don't do that type of analysis anymore because it isn't really backed by science. But still, these are terms that you should know. So why do we dream? Well, Sigmund Freud suggested that dreams were a means of wish fulfillment, that there are some things we can't get in our life, so we dream about it. So I can't win the lottery, so I dream about winning it. I can't actually fly, so I dream about flying. And Freud said, we said, Freud, what about those dreams that make no sense or things I don't want to happen, like in nightmares? Well, Freud says those are things that they are fulfilling wishes that you don't know you have, or they're fulfilling in ways that you just don't realize. It was always circular reasoning with Freud. Rosalind Cartwright suggested that dreams were a problem-solving mechanism where we can think through problems and solve problems in our mind. And that does happen for some of the times where we do come up with solutions to problems that happen because they dreamt about a possible solution. The Hobson and McCarley model is sometimes referred to as the activation synthesis model, where basically there's so much content going on in our brain. There's so much activity in our brain. Images, sounds, memories from the day, memories of the past, our hopes and dreams, what we learn, whatever. All that's going on. It's all this activity is going on. And so our brain, with nothing else to do, kind of puts it all together and makes it into this thing we call a dream. That's a third theory there. Distressing dreams, nightmares versus night terrors. Okay, we kind of use those terms interchangeably, but in psychology, there's a difference. Nightmares happen during REM. Night terrors happen during non-REM. Nightmares are rich and detailed. Night terror would be short, small, but very intense. Duration is long. And in a night terror, it's brief. Movement, there's none from the neck down because it's happening during REM. With a night terror, it can exist and it could wake one up. The big difference, I would say, between the two is this, that with a nightmare, you're dreaming about being on a pirate ship and you're being accused of mutiny, and you go through a trial and you're found guilty, and you are told to walk the plank. You walk the plank, you fall into the water, into the mouth of an alligator, and the alligator spits you out to the moon. And the dream goes on and on and on. Whereas with a night terror, you might have the image of falling off the board and hitting the water, and boom, that just wakes you right up. And that's all there is to the night terror. So that's a difference between the two there. So that is our that's, again, a very, very intense summary of Unit 2. It's a very long, very intense chapter there. Now, I have a few questions here that I encourage you to answer in the chat, and our TA is going to answer them. And also, maybe during the review time, can talk about those a little bit further as well. So let's see here. I'm going to ask in the time I have here 5 questions and see if you can do them. And if you can't, that's fine. It just gives you something to say, okay, I'll need to review that. So what neurotransmitter is associated with mood and appetite? Mood, sleep, and appetite. Okay, so that's your first question. Okay, second question. What part of the brain is associated with emotional memories? Emotional memories. Okay. Third question is, what is the master gland of the endocrine system? What is the master gland of the endocrine system? Your fourth question is, how would you describe the sleep of someone with narcolepsy? When a person has a sleep attack, describe the type of sleep that goes on there. And your fifth and final question is, describe the speed of transmission in the neuron and myelin, the speed of transmission and myelin, okay? And so those are a bunch of questions right there. And if you're answering in the chat, that's fine too. If you're writing them down, say, okay, I'm going to ask myself these later. These are just 5 I just came off the top of my head right here and then. Let's see here. I am trying to see if I have access to the chat here. At least I did. I don't know where it went. Okay. Oops, there it is. Chat. There it is. All right. Looks like there's some answers coming in here. There we go. All right. All right. Well, it looks like Lena's not doesn't need you or doesn't need to be here to answer questions. Lena, you're fired. No, I'm just kidding. All right. I can, with the time I have here, I know I'm speaking on a lag. I'll take any questions with the time here. So, how do we learn the neurons parts better? Well, like I said, there's like so much you can only do in a short amount of time. We do have the study guides. Fiveable does have I'm kidding, Lena. We do have study guides that have visuals that you can help you with that. And as I tell students this is something I strongly recommend. The brain dump. This is one of the most powerful things you can do. You learn, you look at it. Don't just stare at it day after day. Look at, analyze it the next day. Trace it out, draw it out as best as you can. So, and then compare, what did I remember, what did I forget, going from there. So, question about PET, MRI, fMRI, should you know those? The answer is yes. And again, there's only so much I can fit in an hour. So, yeah, as to the answers to the questions I asked, like I said, I just put them off the top of my head. Lena, if you haven't done so, if you could just, I think someone already typed out the answers, but if you just put them up again. So, and a night terror, can the person move? The answer is yes. In theory, a person, they might not always move, but if I'm having a night terror, because I'm not in REM, I am able to move. But if I'm having a nightmare, which happens in REM sleep, I cannot move. Okay, so that's the answer there. All right. Another question, maybe answer. So, yes, and show there will be a live review of this. And like I said, there is so much stuff. No CRAM can cover really a full unit. The the 4-hour CRAM is going to review units 1 through 9, but there's you can't get, even if I taught a whole year of AP Psych, you can't get every single possible question it's going to. So, yeah, if you can cover the parts, the brain scan parts, it's a little bit there, but there's also our study guides do cover that as well. So, I would say that if the scans appear, it's one question maybe. So, fourth stage, basically, when we say the fourth stage in the sleep stages, we're talking about REM. Even though, the stages 1, 2, and 3 go progressively deeper, REM goes back up, but we still call it the fourth. So for that, so all right. We are at the 9 o'clock hour, and again, like I said, it's a lot of stuff. So, and the 6 p.m. Eastern time is in the Discord is when it occurs. Thank you very much. I look forward to seeing you again for the next one, which is, I know it's somewhere. I don't have it right in front of me. But I look forward to seeing you. Have a great night, and everyone do take care. Till then.